Our story today is one of tragedy. We will be discussing bottom-up proteomics with quadrupole filtered high-resolution mass spectrometry. The goal of proteomics analysis is to identify what proteins are in a sample and how much is present. But these insights come at great cost. Let's begin. We begin with a protein in its native state, folded. In our fictional example, each MOBILion team member represents an amino acid. The order, or sequence, of the amino acids is very important as it drives the function of the protein. To confirm this protein's ID, we will need to break it into smaller, more identifiable pieces that are easier to analyze with mass spectrometry. This is a two-step process. First, we need to unfold the protein from its native state. This is called denaturing and is commonly accomplished by changing the pH conditions of the solution the protein sample resides in. The protein is now ready for the next step. The digestion step breaks the denatured protein down into smaller chains of amino acids called peptides. A common way to accomplish this is to use an enzyme. In our example, we will use an enzyme called trypsin. Please note the large sword. This is for cleaving the protein into smaller pieces. But don't worry, this isn't the tragic part. When introduced to the sample, the trypsin enzyme will attack the protein where it finds the amino acids lysine or arginine. At this location, trypsin will cut or cleave the protein, breaking the bonds and releasing a peptide. Trypsin will ignore the other parts of the sequence. Breaking up the protein in this way is important so we can identify the resulting peptides. This is a basic diagram of a liquid chromatograph high-res mass spec system. The LC performs some separation of the peptide mixture, and the ion source adds an electrical charge so they can be analyzed. To understand how a protein is identified, we'll need to focus on three key areas. The first is the mass filtering quadrupole, or quad. By carefully controlling the electric fields within the quadrupole, we can block or transmit the peptide ions. This filter step is important because it allows us to know the mass of the peptide we are analyzing. But spoiler alert, this is where the tragedy occurs. The second is the collision cell. The objective here is to break up the peptide into even smaller pieces so we can measure them. This is commonly accomplished by colliding the ionized peptides with an inert background gas, causing them to break apart in a repeatable manner. The third and final stop is the mass analyzer, where the mass of the individual peptide fragments is precisely measured. We will use this data to piece back together the sequence of the precursor peptide, which we can then use to identify the protein that it came from. Let's get back to our live action example. Here the mass filtering quad is represented by a nightclub bouncer. He can either block ions from passing through or let them pass. The collision cell is represented by a fire extinguisher, where peptide ions are blown apart by colliding with an inert gas. The final step is represented by our shipping scale. Let's see this in action. First, we will demonstrate how the quadrupole filters out ions that are not the target mass. As the ionized peptides enter the quad, they are rejected by the bouncer, and since they have nowhere else to go, they splat on the quad rods. These ions are dead and can't be used for analysis anywhere else. How tragic. Now let's look at an example where the quadrupole allows a peptide to pass through. In this example, the bouncer was looking for the exact M/Z as the peptide, so it allows it to pass. The peptide ion enters the collision cell and is broken up into smaller pieces. These smaller peptide fragments are analyzed by the mass spec, providing what we call a secondary mass spectrum, or MS2. To identify this peptide, we will need to use three key pieces of information collected during the analysis. Since we use trypsin to digest the protein, we know that one end of the peptide is a lysine or an arginine. We know the mass of the peptide because the bouncer only let a specific mass pass through, and we know the masses of the smaller fragments of the peptide from the MS2 spectra. Using these clues and a library, informatics software can determine the sequence of the peptide, which in turn allows the original protein to be identified. Our example only showed the analysis of one protein, but imagine this happening for thousands of proteins. The countless dead peptide ions are the real tragedy of our story. These ions died in the quadrupole because the bouncer wouldn't let them through. The quad mass range can be scanned during analysis to analyze different peptides, but whenever a mass filter is used for specificity, the cost is always sensitivity. These ions passed to the great beyond and were never able to contribute to the identification of a protein. Sad. If that story's got you down, don't worry. There is an analysis approach where no ions die senseless deaths and all are analyzed. Come listen to Dr. Daniel DeBoard's talk on parallel accumulation mobility line fragmentation, or PAMAF, Tuesday, February 25th.